Last lesson we studied how when we take the underlying population with a normal distribution and we take from it several samples, each one with its own mean, and if we then make a distribution of all these means, the distribution is also normal in nature. This lesson we are going to see that this can be generalized for any distribution. This is called the Central Limit Theorem. It says that for any population distribution with mean mu and standard deviation sigma, if the sample size n is sufficiently large, then the distribution of their means is approximately normally distributed as well. Here you can see I put here three random parent distributions. So this one was a uniform distribution, this one was an exponential, and this is a random. If we take several samples with sufficiently large n, and we make a distribution of their means, the distribution of the means is going to be normal in nature. This is very important because, as you know, and this is basically the whole purpose of statistics, one might argue, it's impossible to test the whole parent population. That's why we take samples. And if we start making analysis of these samples, how close the information that we get from these samples is from the reality, from the parent population. Particularly if we're talking about the mean that we calculate from a specific sample, how can we be sure that this mean is close to the true mean of the parent population? That's why we use, for each one of these means, a confidence interval, and we establish confidence limits. They are related. Okay? So we have an underlying parent population. We take one sample. We calculate the mean. We calculate also the standard deviation. And we want to know how close this sample mean is to the true mean. And for that, we need to establish this, the confidence level to begin with. I'm going to explain how this confidence interval is calculated and how it relates to the confidence level that we establish beforehand. Okay? So we will establish a confidence level that have these typical values that goes from 0.80 or 80% to 0.999. What does this mean? Let's say a 95% confidence level. This means that if we take, let's say, 100 samples from the parent population, we would expect about 95 of them to fall into this area over here. Okay? Don't forget, the whole thing is 1. So if we're talking about a 95% confidence level, this area is going to correspond to 95% of the whole thing. And this over here is going to be, these two sides over here is going to be the remaining 5. So 2.5 for each. That's what this means. Okay? Same thing for any other value. As you go down, the bigger this area is going to be. But the important thing is that this is defined by us. We will establish what the confidence level is. Okay? These values are standardized, but if you have any other that is not over here, you can use this. Just go ahead and take a look at it to calculate the value k. And this value k is going to be used over here, right? As you can see, k increases as the confidence level increases, which means that if you look over here, if this increases, the wider this area is going to be. Okay? And from this, if we have a sample mean, x bar, we can say that it is inside these limits if, obviously, the sample mean is bigger than this, or it's smaller than that. We can work this out in terms of the population mean. All right? So if we work in terms of the population mean, we will have this over here that can be put in a single expression, in a single inequality as this. So this side over here is going to be, and this side over here are going to be the two ends of the confidence interval that is going to be established for this particular sample. This is very important. A particular sample that we get from a parent population will have its own confidence interval. So what does this mean? Again, let's go to the example where I took 100 different samples from the parent population. If we establish again the 95% confidence level, we would have 100 different confidence intervals. And we would expect more or less 95% of these confidence intervals to contain the true population mean. Now, will we be able to be sure about that? No, that's why it is a confidence level, okay? For a particular sample that we have, can we be completely sure that the confidence interval will contain the true population mean? No, we can only talk about confidence levels, okay? This is very important for you to understand. Note what happens to the width of this interval in terms of the size of n. As n increases, it's in the denominator, the value of the fraction will decrease. So what does this mean in practical terms? It means that as n increases, the narrower the confidence interval will be. Okay? Since it is inside the square root, you need to quadruple n to halve the confidence interval. Okay? If we work this and we push to both sides the value of the true mean, we will have eventually the mean minus the x bar, okay? The true mean minus the sample mean. Or you can think of it also as the interval width divided by 2, that is the distance that goes from each one of these ends to the mean, which is also can also be described as the precision error or the maximum error. Either one of these is going to be smaller than, if you apply the math, k times sigma divided by square root of n. If we now work this, I'm going to pick e for simplicity. If we now work this in terms of n, you will see, we'll get to this expression, and what does this mean? This means that the size of the sample for a certain maximum error will have to be expressed as this, okay? Don't forget, k is established by the confidence level that you defined beforehand. Sigma is calculated, and there is a relationship between the size of the sample and the maximum error, okay? Moving on. The examples that I showed before relate to quantities that are estimated by a numerical measure, okay, given here by the mean. But there are other situations in which the fraction of a population with a certain characteristic is the thing that matters, okay? In this case, it doesn't make sense to talk about means. It makes sense to talk about proportions of that population that have that characteristic, okay? So that's what we're going to talk about now, confidence intervals for a proportion, not a mean. And if you think of it, the binomial distribution is the distribution to use in these cases, because we need to count x. X is going to be the random variable that is basically the number of times this characteristic is present in a given sample of size n. Okay, so we take a sample of the parent population, and x is going to be the number of times the characteristic, whatever it might be, will appear. So it's binomial. Either it happens or it doesn't. Okay, so it's expressed by the binomial distribution with parameters n, the sample size, and p, where p is the population proportion with that characteristic. You need to know that beforehand. All right. Since it is a binomial distribution, you already know how to calculate the expectation. What is the expectation? Here I represented it as m is going to be the product of n p, which means that now if you don't have the population proportion, and you do have the expectation, you can make an expected theoretical population proportion. You can calculate it by just doing m over n, right? In this case, don't forget, p is not going to be given. It's an estimation, a theoretical estimation given from the expectation and the sample size. What if you have just a sample? Okay, then the proportion p hat is going to be the estimated population proportion, where x is what? X is the observed number of individuals in the actual sample with the characteristic. So again, you can make an estimation of the parent population's mean via the number of individuals in that sample with that characteristic. Okay, this will work in this example the same way as the x bar will work for means. Okay, once you have this, then you have here the expressions that are going to be relevant for you. So the mean number of occurrences per sample, that's the expectation of x, we already saw that, that's NP. The variance of that same x is given by this expression. Okay, they are the same. The variance of the estimated proportion based on a sample is going to be given by this expression. Either one, they are the same. The standard deviation is going to be the square root of that. And finally, the confidence interval for the proportion is going to be given by this expression. Compare it to the one that we use for means, and it's basically the same. Instead of the population mean, you have now the population proportion, and instead of the sample mean, you have now the sample proportion, but the idea is just about the same.